I hope you're doing great. We're looking here at this question. We have 2y prime, which you can say is 2 dy over dx plus y equals x minus 1 times y cubed. When you're looking at this differential equation of the first order, what is it exactly that you're looking at? Like, what style of equation do we have? If you were to start bringing in a representation, we have dy over dx plus, we have something here which looks like a py is equal to qy to the power of m. And you know now what you're looking at. If you're thinking Bernoulli's equation, then you are right. When you're looking at that very right hand part, you can do some substitutions. Z is equal to y to the power of 1 minus n. And what's that n value? It's a 3, which is equal to y to the power of 1 minus 3, which is minus 2. When you're looking here at dz over dx, you know you have minus 2y to the minus 3 dy over dx. But if you want to convert that Bernoulli's form into the linear form of differential equation, how would you go about doing it? There's some items you need to eliminate because you want to have something which would look like this in the end. But we have a coefficient here which needs to be eliminated. We have a y cube which has to be eliminated. You can essentially divide everything by 2, and then you can divide everything by y cube. What you're essentially doing is you're looking at this initial equation, which is exactly as you see it, and you're gonna hit everything with this 1 over 2 y cube. It will eliminate the coefficient of that dy dx, and it'll eliminate the y cube from the right hand side. And what will you get? You'll get a y to the power of minus 3 dy over dx right here. And then over here you'll get 1 over 2 y to the power of minus 2. And then here you'll get x minus 1 over 2, and that'll be it. Or you can say 1 over 2 parentheses x minus 1, but this right here looks good. Now from this part over here, focus right here onto these z substitutions. There's a little coefficient here, minus 2, which you want to hit everything with a minus 2. You can do that. And when you do that, look what happens. It will allow you to bring in these substitutions. Minus 2 y to the minus 3 dy over dx. Minus 2, and that 1 over 2 becomes a minus 1. Y to the minus 2 is equal to minus x minus 1. You can open this up. Why don't you open it up and make it 1 minus x? And that's exactly what it is. Now look, everything will fall right into play by means of those substitutions. Z is equal to that, dz over dx is equal to this. So this is dz over dx minus z is equal to 1 minus x. Now this looks very much like your linear form, dy over dx plus py is equal to q. It looks very much like this. What's your p value here? It's a 1. You have to find your integration factor. It's always e exponent integral p dx. What's my p value here? It's a minus 1. It's not just a 1, it's a minus 1. Minus dx, which you know is e to the power of minus x. This e to the power of minus x, your integration factor, will multiply with everything right over here. And we'll multiply it across. You'll have e to the minus x dz over dx. A minus z e to the minus x is equal to e to the minus x times 1 minus x. So you can open that up, and we will open it up. This is coming here from a derivative of a factor in a product relationship undergoing the product rule. And what is that? You're looking here at the z and e to the minus x. Z e to the minus x. That's exactly what it is. You do the product rule, you open it up, you get that is equal to e to the minus x minus x e to the minus x. Now everything here looks rather easy except for this part right here, because it'll bring in the integrating by parts technique, and that it surely will. But for that I'll need space. Or you know what we can do? We can work it all out, and then we can just combine the answers in. You know, this will go away. Let's work out this. We know this right here is easy. I'll in this space work this out. I have u is equal to x, I have du is equal to dx, and then I have v is equal to integral of e to the minus x, which is minus e to the minus x. Then I'll do uv minus integral v du, keeping in mind there's a minus over here. Minus uv minus integral v du x minus e to the minus x minus integral v du minus e minus x dx. When I do all of that, what am I going to get? I'm going to start posting it out here, then I'll combine everything here. From here, I'm going to get a positive x e to the minus x. Here, this is going to generate a positive integral e to the minus x, which I know by means of its antiderivative will be minus e to the minus x. That minus e to the minus x will hit with this, become positive e to the minus x plus c. But this is coming all out here from just this part right over here. I still have this I have to add in. Remember, I was just doing this right here, this component over here all along. I have to do this as well. And you know, when I bring in that, what is that going to be? That's going to be minus e to the minus x, and then you have all of this coming with it. So let's clean things up and bring this entire expression right over here. So look what has happened. The entire antiderivative of this expression has been brought over here, and it equals z e to the minus x, but I can cancel out things. I have minus e to the minus x, it'll cancel out with this e to the minus x. I can take this e to the minus x on the other side. I'll have z is equal to this divided by e to the minus x and that divided by e to the minus x. From here I'll just get an x. Here I'll get c over e to the minus x, but I can rewrite this again in a better way with everything here in the numerator, c e to the power of x. When I write that out, I know all of this is equal to c, but what was c originally equal to? Look right over here, y to the minus 2. Y exponent minus 2 is equal to that, but why don't we eliminate this negative exponent and just write 1 over y square? 1 over y square is equal to exactly what you see, and that right there would be your function or equation for which this differential equation is true, and it should be right. Perhaps the most difficult part of this was just this antiderivative of this, the integral of this expression and this antiderivative integrating by parts and combining and making sure we don't make any silly mistake with the minuses, but that's about it. So this right here is a good answer, and I like this answer. I agree with this answer. It's right. You can always verify this part over here, and I guarantee you it should be right. I did a lot of talking over there through that, but I believe I haven't made any mistake. If you want, you can also present this answer as this: 1 is equal to y square. You can do x plus c e to the x in a parentheses, and you can bring the y square on the other side. You can cross multiply it here and parenthesize that. But this answer right here and this expression right here, they're both good. They're equally good in my opinion, and that solves this differential equation of the Bernoulli's form. And that's it for this video. Thank you for watching. Have a great day.